What I want to do in this video is show you a series of examples that's going to help you solve very complex mass balance problems. And I'm hoping to demystify some of the kind of like intricacies of solving complex problems and give you a series of problems that will allow you to see the similarities between the different problems, which would hopefully help you understand these kind of situations a little better. First, I want to review the steps you should be taking every time you see a situation that might require a mass balance. If you're in school, definitely read the problem. For some reason, a lot of engineers don't like doing this, but you have to do it, and you have to do it carefully. When you do this, think about the problem. Is it batch, continuous, steady state, transient? What sort of things are you looking for? Then you need to draw a flow chart. Be sure you have mass or volumetric flow rates for every stream and something that indicates the composition of every stream. If you don't do this, you're not going to fully understand the degrees of freedom in your problem. You also need to label the unknown variables on the chart. Just give them simple variables that you can remember as you work through the problem. Then after you know all the number of unknowns, you need to make sure you find an equation or the right number of equations. So for every unknown, you need an independent equation. You can get these equations from process specifications. These might be describing the properties of your system. Maybe you need to meet certain standards. Maybe you have process specifications on the reactors in your systems. You can also look at physical properties and laws, maybe something that has to do with density, ideal gas law relationships, equilibrium constants, etc. Consider your physical constraints. These are like, the sum of all of the masses in a stream equals the total mass of the stream. And then you have material balance and energy balance. Remember, you can perform material balances for each component in your stream and around each mixing, splitting point and reactor. And then you have to solve the equation for unknown variables. In class, only solve for the variables that you're asked. Don't feel like you need to fill in the whole chart. But if you're in a professional setting, of course, you would probably need to fill out your entire process diagram. So for the sake of these examples, I'm going to start with really the simplest problem you can have. This is a mixing problem. I've covered this before, but I want to use it as a starting point here because this is basically the easiest that it can get. So we're going to talk about this in three ways. First, you might have mass flow rates for each component in your system. So these would be in kilograms per second. And this particular example has two components, A and B. I've used the subscripts A and B to indicate mass flow rates for A and B. And then I've also added a 1, 2, or 3 to show which stream it's in. We have two components of our system, A and B, so we can do two mass balances around this mixing point. So here I've said that we don't have any reactions. This is at steady state. So I can perform a mass balance on A and I can perform a mass balance on B. If you had a situation where you had this kind of problem, two of these variables could be unknown. So we have two equations. That means that two of these variables could be unknown. Another way you might draw the same kind of problem is you might be using an overall volumetric flow rate, and you might know the fraction of each of the fraction that A and B contribute to each of the flow rates. So here I've got x A1 and x B1 being the fraction of A and B in stream 1, and I've done this for all of the streams. So this is the same kind of situation. We have two components in the stream. A and B, so we can only write two mass balance equations for this mixing point, one around A and one around B. And so we'll say that X is a volume fraction for A and B, and we can make the mass balance like this. So again, we have two equations, so two of these variables could be unknown, and we would be able to solve this problem. We have also talked about V dot and some sort of concentration. Very often in environmental engineering, we have carrier fluids like water or air, and in general, we're looking at relatively low concentrations of something within those carrier fluids. So while in chemical engineering, mass flow rates of each of the components or fractions of each of the components are very common, in environmental engineering, we more often see these volumetric flow rates with concentrations. And this is true for air and water. So in air, maybe you're looking at one of the criteria pollutants like particulate matter. In water, maybe you're looking at something like nitrate in a stream or in a lake. So next, I have a more complex mixing problem. So we're going to use the exact same principles that we used in our first example, except that we have more equations, more unknowns, but the principles are the same. So here I have some sort of pipe network with a whole lot of mixing joints. And this pipe could be carrying gas or liquid. And basically I just have a whole bunch of mixing points, and I'm going to label my pipe network with volumetric flow rates and concentrations. So we'll do that for each one of the inputs and the output. So here we have two components. We have some sort of carrier fluid, and we have the concentration of something. So we can do two mass balances around each mixing point. So whenever you do this, I really do highly recommend, physically drawing a box around the mixing point to help you visualize the mass balance. Sometimes if you don't isolate these little systems, like the mixing points, you just get confused. So actually physically drawing a box around each mixing point is really going to help you isolate the mass balance equations that you need to be making. So here I've got 4 mixing points. I'm going to label them A, B, C, and D. And I'm going to physically draw a green box around each one of these mixing points. And I'm going to use these boxes to guide the 8 really mass balance equations that I'm going to end up doing. So I'm only going to do mass balances around A and B, but then you can do the ones around C and D. After drawing these boxes, I realized I hadn't actually labeled all of my streams. So I'm adding in labels for those mixing streams. And often you might do this. You might draw a process diagram and then go back and realize, oops, I need to label more streams. I forgot them. So for mixing point A, I can do 2 mass balances, one for the carrier fluid, and then one for whatever C is. B is the same. I can do 2 mass balances for the carrier fluid and whatever C is. And then I will let you do those mass balances for mixing points C and D. on your own. You can pause the video and do it if you want. So in this next example, what I'm going to do is I'm going to show you mixing, or a system that has a mixing, actually a splitting point as well, and a reactor. So in a problem like this that includes a reactor, you're probably going to have some process specifications that you can use to write equations about the flows and concentrations coming in or coming out of that reactor. You're probably also going to have some equations or some information on what's going into your whole entire system and what should be coming out of your whole entire system. And so these are all things you're going to want to include on your diagram. So I'll draw some sort of diagram here. We've got some flows mixing, and then they go into a reactor. Our reactor has two output streams. It doesn't really matter, like what kind of reactor this is. But we have two output streams coming out of this reactor. And basically what I'm going to do is only talk about the mass balance component of this, but realize that you're going to have some process specifications for these kind of systems, and you can use that to finish out or to make all of your equations and finish your mass balance on all of these streams. So the equations, the process specifications, might include variables related, or might include information related to the variables v.3, c3, v.9, c9, or v.4 or c4. You might also have additional information that will tell you something about v.1, c1, v.9, c9, v.7 or c7, or v.8 or c8. Maybe you've got some sort of regulations that you need to meet. Maybe you need to treat a certain volume, or maybe you need a certain volume of product water or product fluid. Okay, so what we're going to do is you can write two mass balance equations around mixing points, around the reactor, and you can write 2+ equations around the splitting point as well. So realize that it's just the best thing to do in these situations. Start from the left, move towards the right, and just identify all of the places that you can do some sort of mass balance around. So what I'm going to do is I'm going to label these areas for mass balance as A, B, C, and D. And I'm going to draw boxes around them in green. Again, I really highly recommend drawing these boxes. It's really going to help you visualize what your mass balance equation is going to be. It's going to help you simplify your thinking so that you can correctly solve the problem. So I'm going to do points A, B, and D. And then you can do C on your own time. So for each of these situations, we can write two equations, one for the carrier fluid and one for the concentration. So again, this looks familiar for point A. For point B, I can write a very similar type of equation, except that I only have one input and two outputs at point B. And then point D is going to be a little different because it's a splitting point. So I can still write the mass balance on the carrier fluid like I normally would, but then realize that at the splitting point, there's no sort of separation or mixing that's happening. So all of those concentrations are going to be 0. So, I mean, these, on some level it seems really, really complicated, but at the same time, it's really just something that you have to break down and think about. And so go ahead and do C on your own. You can pause this video and do this. So you're going to follow this type of method for any sort of system that has a lot of reactors, bypass, recycle, splitting points, mixing points, etc. Provided your system is at steady state, and I haven't really included anything about any sort of reactions in this particular system. So I have one more scenario, and really this is just to help you appreciate the full complexity of these types of problems. So here I've got a splitting point, I've got a carrier fluid, which I'm going to give the flow rate for, and it's got three constituents, A, B, and C, plus the carrier fluid. So I've got that here. I've got A, B, and C denoted by subscript, and I've also included a subscript for the number that I've given the stream. And what you can do here is you can see this mixing point has four potential mass balance equations, one for the carrier fluid and one for A, B, and C. So I'll go ahead and write those here. And realize, like you can just keep going and going and going with these. This is the same kind of analysis that goes into really complicated analyses of entire processing plants. But what's really going to happen if you do have some sort of plant, or maybe you're doing air quality modeling above a city or state, or maybe you're doing a more detailed analysis of rivers or lakes. They all kind of come back to these same principles of mass balance. And every sort of subfield has software that they use to actually do these mass balances. But realize that these sorts of equations and this sorts of analysis is what is underlying those software packages that you might be using in a professional setting. So hopefully that helps guide you in mass balance of complex systems. And hopefully you've now realized that despite the multitude of complex systems that you might see, you're basically going to be going back to the same kind of principles every single time when you're trying to solve these types of problems.